Welcome to this course on storage systems. This is a course being offered through NPTEL. My name is Gopinath. I am from Indian Institute of Science. So, in this course, we will study storage systems, why they are important, why they are needed in the first place, and essentially motivate the study of storage systems, and try to point out some differences between what you might have studied, for example, in networking systems or computer systems. There is some slightly different things with storage systems. I would like to try to understand that part. So, let's get started. So, first let's think about why storage systems have become important in the recent past. For example, if you look at in the 1980s, you would find that processing and storage were together, and somewhere about 1980s, networking started in a big way. For example, the 3 megabit per second Ethernet started in about 1980, and after that networking has become more and more capable, and therefore it is now possible to separate out processing and storage. In the past, it was the case that the storage device was always connected to the processing device through an electrical bus. Now, with networking, it is possible to replace that electrical bus with a genuine networking layer, so that they can actually be separated out and not be constrained by electrical conditions. For example, the fact that you cannot keep the bus, let us say, away from the CPU by more than certain number of meters and whatnot. So, because of this, you will now find that processing, storage and networking are now 3 distinct branches of computer systems with their own styles of design and modeling and performance, etc. Essentially, I just want to summarize like that: fast networks enable separation from processing. And so, storage systems have essentially become decoupled from processing, so they have their own, let us say, logic of development. Now, if you think about storage systems, you will find that you have devices, certain protocols, and certain ways of layering the systems. To give an example, if you look at devices, right, you might have heard about tapes, later you might have heard about drums, which are no longer used nowadays, disks, and now you also have things called solid state devices like flash, and in the future what are called solid state memories. Okay. So, there are also certain protocols. I will go into some of these details later. For example, you can have what is called a network file system storage, or you can nowadays with web scale computer systems, you also have what is called cloud storage. That means that your storage is not locally present, it is available on the web, on the internet. And there is a way to access the storage also, and there is a what is called an API that is often published, by which you can access the storage. In addition, you can have complete systems, large scale systems. For example, you can have the Google file system, which actually is geared for search purposes, or you can have storage for email. If you go to any large scale let us say email provider, they will have storage which is very geared for storing large amounts of mail. Okay. And these things can be quite reasonably complicated. So, there is a special aspects in the design of these kinds of storage. If you think about it, there has been varieties of issues that are involved in designing of storage systems. In the past, one of the major issues was concurrency with CPU. Okay. Basically, because storage devices are slow, because they are slow, you do not want to make the fast guy, the CPU, keep waiting for the slow guy, and therefore you have to somehow make them work together. And so, by definition, once you introduce a slow and fast device, there has to be some element of concurrency. And so, this management of the concurrency with CPU has been an important issue. It is still an important issue, but it has been a very important issue in the past. Another aspect is handling device diversity. You notice that input output devices keep changing all the time, and they come in all kinds of shapes and sizes and capabilities. And so if you're planning to devise a storage system, it turns out that you have to deal with lots of types of devices. As I mentioned already, you can have tapes, you can have drums which are no longer available, disks, and etc. Now if you think about the newer systems, you find that the kinds of things that people worry about is scale. What I mean by scale is, can I make sure that my system can grow from small size system to very large scale systems, like for example, let us say Facebook requires some storage system. Can it scale to that kind of a requirement? It's about distribution. Where should my storage be? For example, it might be that I'm interested in ensuring that some parts of it reside in some places and some other parts reside in some other places for ease of access, for performance, etc. And again, once you start developing storage systems on a very large scale, it turns out you end up getting a lot of errors in the devices. There could be errors in the devices, there could be errors in the possibly sometimes in the protocols themselves or in the systems themselves. So how do you manage these errors? Again, once you have separated out processing from storage through networking, then there is an issue that there are multiple entities in the system. So now security becomes an important issue. Okay. So again, once you have separated out processing from storage through networking, there are aspects of real-time issues also cropping. Basically, because now you separated things out. Now, if certain things have to be done in some version of real time, it could be soft real time or hard real time. You now have to think about how the networking and the storage together provide that capability. Similarly, quality of service also is an important issue. And since these storage systems have become fairly complex, the manageability has become also an important issue. Oftentimes people tell you that if you buy 1 gigabyte of storage, the raw price might be, let us say, $1, but actual final cost that people pay is closer to $7 to $10. That means that the cost can be about 7 times as much as the raw cost itself because of the manageability aspect. Okay. So let us just also look at why storage is somewhat different, okay, from other systems you might have come across. I will mainly contrast it with networks. Okay. Suppose you consider long-term storage. Basically, I want to keep some data available for multiple decades. Basically, I can access something much later than when I created it. Now, what is the issue because of this? My formats and devices can change. As I mentioned, drums are no longer available. Suppose I had stored something in a drum, I cannot access it now. Other issue is the data may not be interpretable unless auxiliary information also stored. What do I mean by this? If I look at a file system, it has certain notions of how to store various parts of a file or the metadata, that is the information about the file itself. That means that I need to know where things are. That means that I somehow have to also incorporate some understanding about the structure of the data that I am storing. So in a sense, that information also has to be somehow stored along with the data itself. So you can sense a certain recursion problem here. Okay. So this is something we also have to worry about. Similarly, let's take a look at security. You might have heard about network security, right? But let's just briefly look at why network security is somewhat different from storage security. Okay. Now, I will contend that network security is across space. What I mean by that is, when there is some piece of information that is being transmitted from one area to another area, typically it turns out it is separated in space, not in typically in time. Of course, it can be in also with respect to time, but usually these are very short durations of time, unless of course you are thinking about somebody sending a network packet to some very far off place like Pluto or some such place, which might take years. Okay. Since we are not talking about those kind of systems, typically network transfers happen within few maximum seconds typically. So the kind of security that is you have to think about turns out to be somewhat simpler, because for example the keys that you have to, for example, use to encrypt things have to survive only few seconds. Whereas suppose I think about storage security. Now I mentioned that you might have to keep data available for decades. That means that this storage security is not only across space. For example, I want to create a document here, I want to read it someplace 100 kilometers from here, that is across space, but also across time. I create some document, I want to see it about, let us say, 10 years from now. Okay. Now, if I am trying to encrypt things, it turns out I might require things called keys, and these keys may also have to survive years. And I mentioned that there is a problem here already of long term storage. So, this we also have to solve. I am just giving you some 2 or 3 important issues which unfortunately have not yet been solved properly, but it gives you some idea that storage is somewhat different. Again, if you talk to cryptographers, they will tell you storage security is somewhat different from network security. Why is that? Because in storage security, what happens is oftentimes you aggregate a lot of information in one single place. That means that you have a lot of ciphertext in one single place, whereas in the case of networks, it is not going to be that dense information in one single place. So, again, there are a lot of differences you can see with networks. You can also see differences between other aspects of computer systems if you think carefully about it. Again, I am going to introduce some aspects of storage and try to give some high level ideas in this particular class, and then we will look at most of these things in some detail later on. Let us just look at what is the issue with storage. There are 2 major functions that you have to do in storage. One is naming, one is storing. That is, first you have to give a name to an object. Now, what is interesting about this is that giving a name to an object itself can involve processing. For example, you might keep an index so that I can access things faster the next time around. That is one possibility. Other possibility is that the name itself may be computed based on contents. Sometimes you have what is called content based storage, by which the contents are basically used as a way to locate the information you are looking for. Okay. Now, this looks a bit strange, but basically what I can say is that you can store some file by looking at its contents and actually computing some kind of a hash on it and use that as a name. Okay. And later on that name is used to access it. Okay. The storage system can be asked to retrieve that information based on that hash. Okay. So, this also is possible. Now, this is one part of the thing, this is naming an object. So, this as I mentioned earlier can involve quite a bit of processing. Okay. Second thing is storing an object. Now, it turns out this itself can involve doing other reads and stores itself. So, there is some interesting aspect relating to this, I will come to that later. Storing also can involve significant computation. For example, I can compress things before I store, I can encrypt it, I can do coding, or sometimes nowadays, because of the large amounts of storage that is being generated and stored, you oftentimes do something called deduplication. That is, you want to remove redundancy. That is, you have some piece of information, you want to store it. What I would like to ideally do is see if some part of the information I am trying to store actually is already existing in the storage system, so I can eliminate having to store that part. Okay. That also is there. So, this also becomes quite a big thing. That means I need to actually check whether I already stored part of it somewhere. Okay. So, this is also a big issue. So, basically storing an object itself can be substantial amount of time. It can take substantial amount of time. Okay. Other aspect is that I need to keep auxiliary information about an object. For example, when did I create an object? When did I let us say add something to it? Okay. What is the size of the object I have kept? And nowadays this is becoming also important, what is called, it is often called provenance, that is, how did this object come about? Okay. So, I need to keep this information because oftentimes this is a critical piece of information. For example, in legal areas, it is important when something was created, when some mail was sent, etc. All these things are important. Okay. So, in a sense, I need to keep some auxiliary information about the object, and so there is an issue about metadata and data. Okay. Again, the metadata also has to be stored. Again, you can see some elements of recursion out here. You can even go further. Where do you store the metadata, information on metadata itself? Where is it stored? Okay. There are other issues like, for example, if I lose metadata, am I lost? Is that an issue? Or if I lose the data, am I lost? Which is a more critical thing? Do I need to have different ways of protecting metadata versus data? These are also issues, some things you might have to think about. Again, I mentioned naming and storing are important, but if you don't access the information, then you are not doing anything useful. Finally, you have to do some access. So again, here is where the device specific aspects determine the speed at which you are accessing it. For example, your accesses could be sequential, non-sequential, or random. And depending on whether it is sequential or non-sequential or random, your performance also can change. Your writes can be in place or out of place. Again, there are different devices which have different aspects relating to these things, and this your storage system has to make sure that you are doing as well as you can given the devices you have. Now, as I mentioned, a lot of people are generating a lot of storage, a lot of information, they are storing it. So basically, it has to be persistent so that I can access it later. So once you have large persistent data structures, if you do want to do some processing, I can't do it directly on the storage devices. I need to bring it to memory. So usually because of this, you have what is often called in-memory copies and on-disk copies. Once you have in-memory copies and on-disk copies, you might have issues relating to what is called atomicity and consistency. We will discuss this in some detail later. Again, once you have large persistent data structures, you need to take into account algorithmic aspects carefully, especially about how to access them, how to store, etc. Because the number of objects can be in billions, such objects can be in multiple gigabytes, and as time progresses, as the scale keeps changing, you need to keep developing newer algorithms. For example, when I first started using computer systems, I think the maximum number of size of things which I used to play around with was probably in the kilobytes. But nowadays, playing around with megabytes is quite common, right? Or you can take a simple example. If you look at any email system, you will find that the mail directories can have thousands of messages. And typically, if you use certain kinds of formats, the mail dir format, for example, each message is a file. So that means that a single directory can have thousands of messages. Now, if I create a file to ensure certain consistency requirements, I need to log the directory. Now, if two or three parties want to concurrently create an email message, right, then the same directory can become locked-bound. Okay. So there are issues with respect to locking, etc. that can come in. Again, this happens because of the scale. Once you are working with small scale, it's not a problem, but once you start going to larger and larger scale systems, these things become extremely critical. Again, with web level storage systems, this is absolutely critical part. You have to take it into account as part of the as a starting point of the design itself. And for that reason, you will see many newer models. For example, key value stores, etc. have become popular since 2000. We will discuss this key value stores in some detail later. Again, I am just giving you high level ideas about why this is a slightly different kind of systems than what you have seen before, and so I am just trying to motivate study of storage systems independent of other subsystems you have. Just to give a quick idea about some of the structures that we often deal with in storage systems, I will give you two examples. One is the ext2 file system. I have taken this figure from the Wikipedia article on ext2fs. This is what is called, the data actually resides in these blocks, what are called the direct blocks or the indirect blocks or the double indirect blocks. And these are all basically indexing structures, what you see here. These are all the indexing structures, and this particular design is from a file system, ext2 file system, that has been used in Linux since 1992 or so, or 1993, and this itself comes from a file system called the BSD file system that was designed in about 1982 or so. And the basic idea in this particular design is to ensure that if you have small files, you can store them directly in direct blocks. Each direct block is about, let us say, 4 kilobytes. So for example, you have a file of only 8 kilobytes, you just need 2 direct blocks, and rest of it is not used. None of this is needed. Okay. Whereas if you want to go for bigger and bigger files, you first finish off using all the direct blocks. Once you're done with the direct blocks, then if you still need more space, then you use one level of indirection, one additional level of indirection. This is called the indirect block. Indirect, okay, I should call it, I think there should be a small difference. It should be called direct data blocks, it should be indirect data blocks, double indirect data blocks, and this should be called indirect block and double indirect blocks. Okay. So this is an indirect block, and this will actually have pointers to the indirect data blocks. Okay. And if you run out of this, then you go for one more level of indirection, and you will see that typically you have about 8 of these direct blocks. That's about 8 into 4, 32 kilobytes. If you go beyond it, then it turns out that each 4 kilobyte indirect block can store about, let us say, if you assume about 4 bytes per each indirect data block, about 512. Okay, so you can see that you can have about 512 indirect data blocks. So 512 into 4 kilobytes, that will be about 2 megabytes. So this will be 2 megabytes. Okay, so up till 2 megabytes you can use this. Once you go beyond 2 megabytes, again this can go into ability to store about gigabytes. And this is a design which is trying to solve many problems, because I often have small files and big files. I want to see if I can have some structure which can save all these things that can be used to store small files as large files. But you can see that there are some difficulties with this. A good example is, suppose I have a multimedia file. The multimedia files are generally time sensitive. That means that if the time taken to access these double indirect data blocks is different from time to access this or versus this, then my design of my real-time system for showing this, for looking at this data and showing it for some multimedia purpose, for example, it's going to be more tricky. Why is that? Because to access this, I need to go through one level indirection followed by another level indirection. So these add latencies to my access here, and therefore it can create certain complications. Okay. So this is an example of a file system that was designed before large multimedia file systems, large multimedia files became very common. Nowadays, people would like to design something more, some of the structures by which all the data blocks, whether all the data blocks are about the same place, require the same amount of going through indexing structures. Okay. They don't require different types of different units of different amounts of indexes to be traversed before you get to the data blocks. Let's take another example to just see what kind of file systems can be existing, storage systems can exist. This is an example of a Google file system. Again, I've taken this picture from Wikipedia, and now this particular file system is geared for doing search. I think we're all familiar with Google search, and the issue is that they have very large amounts of storage that has to be searched fast. In addition, the amount of stuff they have is very huge, so it's important that you optimize the system for this particular purpose. So basically, the Google file system is geared for doing one thing, mostly read-only data. I want to search it fast. And how is it done? What you do is you crawl the web, take all the data that you crawled and put them into different files, and then each file is split into large chunks, let's say 64 megabyte chunks, and the master keeps track of the metadata. That basically it is the keeps track of where the chunks are. And the chunk servers are machines which are able to access those chunks, and an application, for example the search application, Google's search application, it will talk to the master and say, I want to know some information about a particular file which has the information which I am looking for with respect to some search query that has come in. The master gives you some metadata about where it can access, where it can find it, and this application directly accesses the chunk servers. That is, once you get information from the master, it can directly go to the chunk server, doesn't have to go to the master again. Okay. And because they are operating at a very large scale, it turns out that there are problems of reliability, that is, there are disks which are storing these things, let us say. These disks can fail. So, for that reason they need to have redundancy in the system. That means, for example, chunk 1 is, there is one copy here, there is another copy here. Similarly, chunk 2 will be having another copy. So, in case one of the copies fails, that disk fails, then you can actually, the master can redirect you to some other chunk. Okay. So, you will find that the Google file system has a different notions of what to from a design point of view than what a ext2 file system has got. Again, in this particular course, we will try to explore some of these aspects in some detail. Another aspect that we have to think about in storage systems is that the storage stack is fairly deep. Okay. Basically, because there are various types of abstractions. We can have what is called the device abstractions, block abstractions, file abstractions, and even application level abstractions. I think this may not be that well, not that clear. So, I just want to mention that if you write a program in C language, in libc for example, there are specific functions which actually buffer what you are taking from the storage system. Okay. So even application also can be the picture. Now, there are each of these abstractions, there are even more sublayers. For example, if you take a disk, like a device for example, there is a protocol called SCSI, SCSI, Small Computer Systems Interface, and this device, if you look at it carefully, the software stack that is used to access this device has multiple sublayers. For example, it can have something called an upper layer, a mid layer, and the lower layer. The upper layer essentially takes care of highly device specific aspects. For example, tape has to be accessed differently from a disk. Tape has some notion of a rewind, whereas a disk does not have it. Okay, those kind of aspects like rewind etc. are device specific, they are handled here. Mid level basically is protocol specific, this is actually the SCSI protocol itself. The lower layers basically are the physical communication layer. For example, your SCSI device can be on a physical electrical connection, or it can be through a network. So, this part of it is basically the communication part. Again, continuing on the same communication part of it, it turns out if you want to really have your storage system scalable, you need to have essentially the network stack part of the storage stack, because my storage is across multiple devices which could be in different data centers or geographically separated by thousands of kilometers. That means that the network is a part of the storage stack. So, you might have heard about the 7-layer storage stack, the Internet ISO standard. That means that almost all of this also has to be part of the storage stack somewhere in the picture. Okay. So, for quite a long time, most of the stack was in the kernel, but again, given that the networking has become sufficiently fast to separate processing from the storage, a good part of the stack is now migrating out of the kernel. A good example is Google file system. You will see that most of the things that they do is out of the kernel. It's not really everything. Not everything is done in the kernel. Okay. Okay. Let's just briefly look at some aspects of storage. First thing I would like to mention is that concurrency arises naturally. Why is that? Because there is a wide disparity in speeds of memory and storage. So, if you do not want one guy to keep waiting for the slow guy, you should let everybody keep going at their own pace. What you have to do is you have to mask slowness of storage somehow, very critical. So, you want to make processing and storage go at their own rates, and therefore, you need to come up with some new mechanisms like interrupts or sometimes polling to signal completion of slow storage operations. And this is the historic reason why operating systems actually developed, because you used to deal with devices with highly different let us say speeds, and to manage those things, the whole discipline operating system started with this. Okay. And other aspect of storage is that you are storing something because you want it to be persist over time. That means that typically it increases with time, but at the same time, not all the stuff you have stored is important. Somehow there has to be some notion that some parts are important, some parts are not that important. Okay. That means that you need to find a way of categorizing storage as something that has to be in fast storage and slow storage. Therefore, caching and tiering arise naturally. These are important aspects that have to be there because we are dealing with slow devices. Okay. Now, if you think about it, it turns out that there are some serious constraints either of speed, capacity or cost. As I mentioned, storage keeps increasing over time. That means that you can't keep on investing too much money in it because it just keeps on increasing. Okay. That means that you preferably would like to have low cost storage. Okay. But it turns out that low cost storage is in conflict with speed, and so you can't have both high speed and low cost. Similarly, you can't have high capacity and let us say high speed and low cost. It is not possible. So, you have to choose two out of the three typically. Okay. And in storage, typically what we do is we decide to concentrate on cost a bit more and capacity a bit more and use caching and other methods to take care of the speed part of it. So, this is what we typically try to concentrate on, make sure it is as capacious as possible and as low cost as possible, because the storage amount keeps on increasing with time. There is no way to let us say make it keep decreasing with time, which is not possible. So, that is why I somehow have to make sure that it is low cost. Again, to reiterate, storage is often the slowest component, therefore you need to use caching as an important principle. And in addition to this, you might want to do some other interesting things. For example, if you have a single device, you may want to merge requests so that it is possible to deliver each request more efficiently combined together than singly. Okay. Other thing you can do is to schedule requests in an order that is best with specific device. What I am trying to say is that in computer architecture you might have heard about out of order execution, but it turns out that that came out much later, but in storage it turns out that this is a very important and commonplace thing. You need to do out of order execution because you want to make sure that the device is able to respond to requests in the way it finds it best, rather than the way the application or multiple applications are asking for it. Okay. So, the higher level software has to work around this aspect. If you need a particular order to be honored, it has to be left to higher level software. Okay. Again, we will come to this later. This is concerning when we talk about atomicity or transactions, etc. We will find that this is an important issue that we have to worry about. Usually, what I am trying to say is that the semantics of storage, it is as weak as possible, so that your system is as high performance as possible. Okay. So, this introduces a lot of complexity into storage, a lot of complexity. Okay. And for the same reason, you often do what is called asynchronous processing. That is, you initiate an access and you do not wait for it, and you hope that somehow you will figure out when it is finished and later do something with it. For example, you might have some libraries called AIO libraries, which help you to do this asynchronous processing. Again, because of the slowness, you would like to exploit parallelism across multiple devices or threads, and if you have multiple disks, it is possible. With multiple chips nowadays with solid state devices, you can do it. In the future, we will have something called storage class memories, and this also will become extremely important. Again, the way to manage so many disks and so much IOs happening at the same time is through some models of threading in your operating system or in your application. Either application can be multi-threaded or the kernel can be multi-threaded. So, it also introduces additional levels of complexity because you need to actually manage the parallelism across these devices. Okay. So, again, all of this is coming because storage is often the slowest component, and therefore you need to do a lot of things to work around this particular problem, and so your software tends to be slightly more complex. Again, there are issues with respect to the kinds of devices. For example, some of the software or much of the software that has been written so far assume that disks are being used. Therefore, there are some notions of circular tracks are there, so that when you access something, you will find that something near each track, for example, is preferable to access something close by track than something else. So that is essentially an assumption about the disk itself, whereas this particular assumption may not be true when you go to things like solid state disk or storage class memories. So some of the assumptions that you are making sometimes unfortunately are let us say deep down in the software's model of how to access these storage devices. In the future they might have to be decoupled so that this kind of things don't create complications. Again, for the same reason, because of slowness of devices, optimization of accesses are important. For example, what to cache, what to prefetch. However, usage patterns typically are not known a priori, and it's very clear there are big differences in performance whether sequential access or random. So, system actually can be perceived to be very slow if too many on-demand migrations from slow to fast tier of storage. There are a lot of latency delays. Again, just as I mentioned earlier, optimization is critical and they sometimes override semantics. Out of order processing is typical, and therefore there is complex high level software. Again, and this is what I already discussed before. So because of these reasons, it's quite important that you can learn on the job. Okay? That is, you see certain accesses, can you make sense of it? And typically most storage systems have simple and robust methods so that you can somehow work around this slowness of devices. For example, if you take any file system, if you access any part of a file, there is always something called read ahead that happens. And these are a very simple and method to make sure that if your accesses are sequential, if you do read ahead, then you will not suffer latency for the thing that you already read ahead. So simple and robust methods are widely used in storage system, but I think as time progresses, probably even more complicated or complex models of learning the kind of application accesses that are taking place have to be investigated and incorporated into storage systems. I think this work is just about to be incorporated into storage systems design. Now let's look at one other aspect. This is concerning storage protocols. Okay. Now if you think about a network protocol, usually each party sends something and waits for the other. Here it turns out that instead you have an interrupt driven model. Okay. Basically, given that storage devices are slow, you don't want to keep waiting for them or keep polling them because it's too expensive. Again, to appreciate the difference in the speeds, memory can be, let us say, about a few nanoseconds, whereas access to a disk can be in the region of milliseconds. It's about, the difference is about 10 to the power of 6 or 10 to the power of 5. And so you cannot really afford to wait or poll. Okay. You need to actually tell the storage system, when you are done, tell me that you finished. Okay. So this is a typical model, and therefore what happens is that once the access is completed, you interrupt the CPU, but the CPU, if it gets interrupted too often, it creates some complications. Therefore you often create what I would call as an agents which take care of interrupt processing, and the agent typically that is used is what is called a host bus adapter. This is the name which is sort of historical, but basically because these sit on the electrical bus directly, that's why it's called host bus adapter. These are agents which insulate the processing unit from the interrupts that are happening because of storage access completions. So now, because of this host bus adapters, it turns out that you can do some other additional useful things, just like networking has segmentation and reassembly, right? Because networks have to traverse different types of networks with different characteristics of different useful sizes of network packets. So they also do segmentation and reassembly. Here also we do the same thing. So the HBA actually does some type of segmentation and reassembly, which helps in efficient ways of transferring information from storage device to CPU through the HBA. Okay. The other thing that is very common in storage protocols is what is called split trace transactions. Typically you have a master and slave, and usually the idea is the master regulates how the bus is used. But in storage systems, there is a slightly different thing that happens, because the master cannot, again as I mentioned, cannot be keeping on waiting and polling. Okay. So that means that if, for example, our disk, it takes let us say a few milliseconds, okay, to seek to the right spot, okay, then it itself will try to grab the bus. It does not have to go through the master to get the bus. Okay. In a sense, there is the protocol has been designed in such a way that the master initiates it, but the slave becomes the master, essentially the owner of the bus based on when it completes. Okay. So you will see some subtle differences between the way protocols are actually designed in the storage systems. Okay. Another aspect that is critical about storage is that the protocol endpoints should be preferably be virtualizable. What does that mean? Notice that SCSI devices preferably should be placed on electrical bus, that is you are trying to keep it very close to the processing unit because you can't handle too much latency, therefore you actually want to physically keep it as close as possible to the processing device. This happens in large scale servers, or you might want to keep the SCSI devices on a network or internet itself, okay, if somehow I can handle physical layer properly. Now this is possible if it turns out the protocol endpoints are virtualizable. What it means is that they speak a certain protocol, and all that matters is what happens on the protocol data units. If those things are handled, then these SCSI devices can be essentially used in various different places in various different formats. Okay. So again we will look at this a bit later in some detail. So one thing I would like to mention is that devices can have arbitrary structure as long as they speak the storage protocol. Here I am using SCSI for specificity. They can have arbitrary structure. What I mean by that is, if you have, for example, a very large scale storage system, I can have a big server, and this big server can manage huge numbers of disks, and it can pretend as if the big server plus all those storage devices, all of them constitute one big massive disk. Let us say the massive disk can be, for example, nowadays we have 1 terabyte disks, 2 terabyte disk. Suppose I want to create a 100 terabyte disk, then I can have let us say 100 of 1 terabyte disks, and this big server using some electrical bus or whatever can pool all those devices, and it can pretend as if it is exporting a 100 terabyte disk, and this big server together with the disks can be thought of as a single device, and users using this particular virtual disk, they don't have to know the structure of that it's actually a server with multiple disks sitting somewhere, etc. All they know is that it is a SCSI device and it speaks the SCSI protocol, and therefore it can, let us say, work with hosts. We just assume that it is a SCSI device. They don't have to know anything about how it's actually constructed. So this virtualization is a very important aspect of storage systems, and it is very extensively used. And if you look at SCSI protocol, the reason why it has survived so long, because for example SCSI devices started coming out in 1980s. The first version came in I think 1980, about 1990 I think SCSI 2 came about, and SCSI 3 has been in existence in about 2000, and one can see that these kind of devices are let us say widely used precisely because they can be virtualized, and therefore you don't lose your investment with respect to your host devices, how they actually talk to these devices. Okay. For example, HBAs for example don't have to change, because as I mentioned to you earlier, CPUs have agents which actually talk to the storage device. This HBAs for example, they actually don't have to change at all, because the devices, if they are virtualizable and they export a SCSI interface, HBA doesn't have to change. Okay. So all I wanted to point out in this particular slide was that the protocols that you see in storage systems are often of a different nature than from what you see in other areas like networks, for example. And I have not mentioned some other aspects here. For example, security. If you look at storage protocols, there are aspects relating to security that also have to be taken into account, and typically they will be running on top of the network protocols. Okay. And there are some specific protocols for storage security. Again we will briefly look into it at some point, at some suitable time. Okay. Okay. So I think I would like to summarize what we have looked at. First of all, the storage system design has many ramifications of the rest of the system. Why is this? Because if you look at storage systems, they are often used to store some critical information, like for example in the paging system, if you talk about virtual memory subsystems, the storage system actually stores those pages that has been swapped out. So if that swap device is not fast enough, then your performance of your programs or applications can be slow. Okay. So that's the reason why you have to make sure that your system design is properly well thought out, and so basically you need to provide abstractions based on application needs and the type of devices you have. This design has to be sensitive to cost and the types of devices that you have and how to manage them. You need to introduce new abstractions with time. A good example is key value stores that have become popular with web scale systems. You will notice that key value stores were not used seriously before 2000, but once search became very important, key value stores became quite critical. And these storage systems also have to scale to support large scale computing systems, because without the scalability, then the current web scale kind of systems cannot really be used at all, and so they become extremely critical to the whole design of these systems. And so I think I'll conclude at this point. I think in next class what we'll do is we will look at each issue, okay, we'll take each issue in sequence and study it in some detail, and so that you get a complete perspective about this resistance. Okay. Thank you.